In this video, we're going to discuss the idea of minimum spanning trees. And I've drawn out a sample graph here to demonstrate the idea of how minimum spanning trees work and generally a way that we can construct them using an algorithm known as Kruskal's algorithm. A minimum spanning tree is basically a structure that exists for graphs and exists in situations where we have a weighted, connected, undirected graph. So we've talked about these different ideas before, right? The graph is connected because all of the nodes are reachable from any of the other nodes, right? And this graph here is weighted because every single edge has a weight associated with it. So for instance, the edge from 0 to 1 has a weight of 4. We could consider weights to be things like costs, right? And oftentimes we may want to figure out how to connect the different edges together at the lowest possible cost. And that's really the idea of a minimum spanning tree, is that I want to be able to connect all of these different nodes together using the lowest cost edges. And when we do that, we're going to construct a tree. It will be a graph that has no cycles inside of it, and it will be connected, and it will have the lowest possible weightings of edges. And that's what a minimum spanning tree really is. It's a tree that connects every node in a graph using the smallest possible combination of edges, so the smallest possible weight of edges. So that's the idea of a minimum spanning tree. Now, understanding that, let's talk about how Kruskal's algorithm generally works. The idea of Kruskal's algorithm is pretty simple. Basically, we're going to sort all the different edges that we have in a ascending order, so smallest to largest. We're then going to pick the smallest edge. We're going to check to see if that forms a cycle. If it doesn't form a cycle, we include it in our minimum spanning tree, and we continue this until we've constructed a tree. So let's actually apply this algorithm here. When we take a look at this graph, the smallest edge that we have is this edge from 7 to 6. So the very first thing that we place in our minimum spanning tree is that edge. So we have 7 and 6. Which has a weight of 1. We then take a look and we see a few different edges that exist. So we have, two edges that have a weight of 2. That's the next lowest value. So the question would be, which one gets taken next? And it doesn't really end up mattering which one gets taken next. We can take either one in either order, and that's okay. So in this example here, I'll just take 5 next, and then I'll go ahead and take the one from 2 to 8. So we have this here, right? And you'll notice that when we start, nothing really has to be connected. We can have all these different pieces, and we're just going to trust that everything ends up connected at the end, right? So we've taken this edge here, we've taken this edge here, we've taken this edge here. Okay. So next thing we need to do is search for anything that is, the next size up. So there's no 3 weighted edges, but I have 2 4-weighted edges. I have 0 to 1 and 2 to 4, or 2 to 5 rather. So I'll take 2 to 5. 2 to 5 seems like a good one. And then 0 to 1, that seems like okay. So we'll take 0 to 1, which has a weight of 4. So these 2 edges have been taken. And now we keep looking, right? No edge with a weight of 5, but we have an edge with a weight of 6, right? Which is 8 to 6. And the question is, do we take it? If we take the edge from 8 to 6, notice that it creates a cycle. So just like pretend that I were to take this edge here, right? What would happen is now we have a cycle. I can now start at, say, 2, and I can move my way to 5, to 6, to 8, and back to 2, right? So I can go back where I started, traversing unique edges. So this is a problem. Since we're trying to create a minimum spanning tree, we don't want any cycles to be in it, right? So in this case, we can't take the edge 6. So we're not going to be able to take this edge at all. However, there's one for 7, which goes from 2 to 3, and that one is okay. So we'll take that one there, which has a weight of 7, right? And then we continue on from here. So we can see that we have an edge for 8 between 1 and 2. So we can take that edge there. So that would be 8, right? And then we're continuing to take a look. I have another edge for 8, which is 0 to 7. But if I take that edge, I would then have a cycle, right? I can start from 0, go to 7, 6, 5, 2, 1, and back to 0, right? So we can't take this edge here. That's not going to happen, right? So then we continue to look. I could connect 3 and 4 with a weight of 9. So we haven't put 4 in yet, so we can now put it in with a weight of 9. That's great. And then we continue on through here. I see that I have one with a weight of 10, which is between 4 and 5. And I can see that that would create a cycle, so I can't take that. We have one from 3 to 5, which would also create a cycle, so we can't take that. I have one from 1 to 7, which would create a cycle, so I can't take that. And I have one from 8 to 7, which I forgot to put a weight on, but it doesn't actually matter because it can't be taken. It would create a cycle. And in turn, this would be the minimum spanning tree that we get. So this right here is a tree. You can see that it has generally no cycles inside of it, right? And it's going to connect all of our different nodes together, right? So we can see that we can reach all of our different nodes from any of our different starting nodes. So this in turn is actually constructing a tree for us, right? So we see that this generally looks to be a pretty decent construction of a tree, right? Now I will note that there was a complementary tree that we actually could have taken based on which of these 8 edge nodes we decided to take. Another option for our tree was actually that we could have had 0, which has a weight of 4, to 1, and then we could have had a weight of 8 that goes to 7. And then that would have just varied it like this. We would have had something like this, and then something like this, and then, it would have gone up to 2, and then over to 8, right? And then to 3 and to 4, right? So there's technically 2 minimum spanning trees that exist. They have the exact same weights to their edges, right? So this only really happens if we have, 2 edges that are of the same weight inside of our graph. In that case, we may have, multiple different minimum spanning trees. The main point here is that no matter which minimum spanning tree we have picked, we've connected all of our nodes together with no cycles, and we've minimized the edge weights here. So you can see that all of these edge weights were the minimal choices. So this is one example of how we could create a minimum spanning tree. This is, again, using Kruskal's algorithm. In the next video, we'll take a look at how we can actually implement Kruskal's algorithm. And then after that, we'll take a look at an alternative approach known as Prim's algorithm. So thanks so much for watching this video, and I'll see you in the next one.